So what happened on Friday was I went through the first velocity worksheet there, the one that says, what's the title in the top there? And there's like a numbers rather, like 2.3. So the first one there that says velocity 2.3, I sort of went through that as a group. And then I gave you an opportunity to do some sort of self-study, like you're going to have to do in your future studies. And I said, you should read through this one here, which is 3.3 velocity, which is a little bit more mathematical in nature. And then there were some questions sort of at the end to sort of summarize your reading. So let's just go right to those, and we'll quickly go through those before I get into sort of today's stuff. So, number 1 says, defining acceleration verbally and mathematically. What type of quantity is acceleration? What is deceleration? So acceleration verbally, you would have something like, it is the rate of change of velocity. Rate of change of velocity, or how fast the velocity changes. But Renee, I know. So what is acceleration? It is the rate of change of velocity. Rate of change of velocity, or in other words, how fast the velocity changes. How fast the velocity changes. Mathematically, then what the formula, what would it be? Yeah, delta V over delta T. Change in velocity divided by change in time. Delta V over delta T. What type of quantity is acceleration? It is a vector. How come? Because it has direction, that's right down. And what is deceleration? Negative acceleration. Negative acceleration. Okay, let's move on to number 2. A certain car is accelerating at 5 kilometers per hour per second. Explain what's happening to the motion of the car. What's happening to the speed if the acceleration is 5 kilometers per hour per second? Well, Laura, what's happening to the car? Let's see.
Its speed is going 5 kilometers per hour each second.
Every second, exactly. Every second, its speed is increasing by 5 kilometers per hour. Every second, its speed is increasing by 5 kilometers per hour. Are these hard? It really shouldn't be. I mean, these are just sort of, this is review. I mean, yeah, you might have a little trouble with some stuff, but it should all make sense when we're done. Number 3, give an example of a moving object that has a velocity vector and acceleration vector in the same direction. Go ahead. You know, accelerating forward, speeding up. Yeah, the car, is it already moving? Or does it have to be from rest? Well, it has a velocity vector, so it has to already be moving. So a car speeding up would be, or a train speeding up. Okay? So it's already moving, it has a velocity, probably forward, and then it has an acceleration, it speeds up, so the velocity and acceleration are both in the same direction. What if it has a velocity acceleration in opposite directions? Use Hannah's chain. It's moving along, and it slows down, right? The velocity is still forward, but the acceleration is now backwards, right? When objects have when the velocity and acceleration vectors are in the same direction, then the object is speeding up. When they're opposite directions, they are slowing down. Question number 4 says, can an object be moving at a constant speed and accelerating? I hear yes. Around the corner. And the direction is changing, right? If you're going around the corner and the direction is changing, and you're maintaining at constant speed. You're cruising along the highway at 100 kilometers an hour and you go around a corner. Also, yes. Absolutely. Going around a corner at a constant speed. Number 5, what would be the shape of a speed versus time graph for an object in free fall? Free fall, the opposite is it speeding up? What would be the shape of a speed versus time graph for an object in free fall? So the object is speeding up, eventually reaching terminal velocity. But as it speeds up, the speed is increasing. Is it negative speed or positive speed? Negative. How come? Velocity. Right you are, Dan. So, as the velocity increases negatively, what does the velocity time graph look like? Like so? Is it, you can never draw that? Like even after I show it to you? Would it be straight at the start B or would it be curved? Why do you say curved? But remember, this is the velocity time graph, it's not the displacement time graph. Okay, let's just for a moment assume no air resistance and it does not reach terminal velocity. It goes faster, 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 faster. Let's assume that for a second. Straight or curved? Again, let's assume no air resistance. So it's in fact speeding up, going faster, faster, faster. Remember, this is velocity time graph. We're graphing the velocity. The velocity is speeding up. Is it speeding up at a constant rate? As the lone wolf, she says yes, and she's right. Why yes? Yeah, and what is that rate that it's speeding up at? What's the number? Minus 9.8, right? Right? Is it not speeding up at minus 9.8? So if there's no air resistance, then it's going to be a straight line having a slope of minus 9.8. B is right. It's not. Right? Because there is that air resistance. So in fact, it's speeding up, but it's actually, as it speeds up, the rate at which it speeds up actually slows down. So in fact, when air resistance is taken into account, you're right. It is like that. But I don't think for the same reason that you had it curved. Am I right? Yeah. Well, again, it depends on which one. If you're saying no air resistance, it would be this one. It'd be a straight line. But if you are including air resistance, it would have to be curved because it's actually slowing down its rate of acceleration because of air resistance. I think you said it was curved because you thought it was displacement, right? Yeah. And in fact, what shape you should have given me should have been this one, really, right? Yeah. That's okay. We're here to make mistakes. I tell you guys a thing, I don't ever lose. I either win or I learn something. Did I say that? Number 7 seems to be cut off on mine here. Is it cut off on yours? Yeah, there's no number 6. I think I cut it out. Number 7 says, what is the relationship between speed and velocity? This one you should know. Velocity is simply speed with direction. Speed with direction. Got that right? Number 8. Answer the following by referring to figure 5. Over which interval does the object have its greatest velocity? So we're looking at this picture right here. Oh yes, I remember this. What kind of graph is this? That's not the one? Oh, that's this 310. Oh, it's the page before? 3.5. Okay, so that's this one. This one here, right, Dan? Okay. Number 8. Answer the following by referring to figure 3.5. Way too much mistake. Seriously. It's not going to work. It's simply not. I know it's still close to summer, you're not used to it, but you got to get back into school, okay? You got it. It's hard stuff, and explain it 8 times It might be necessary, but if I run out of time, you're only going to hear it 6 times. You've got to listen. Over which interval did the object have its greatest velocity? Okay, so this is actually a position time graph. So the velocity is represented by the slope. So where does it have its greatest velocity? Where it has its steepest slope. So that would be, I would say between, I heard someone say 4 to 6 seconds. 3, 5. Back a page. Between 4 and 6. Over which interval was the object's velocity decreasing? So it's decreasing when the slope is getting less steep. And when does that occur? 6 to 10. It's getting less steep here. So it's decreasing in speed from 6 to 10. And when is it increasing? That's at the start. 0 to 4. Velocity is speed with the direction. I know.
4 to 6, 6 to 10, 0 to 4.
Okay, I'm on number 10 now. For those of you following along. Or I guess for those of you not following along. Those of you that are following along, no, I'm on number 10. Number 10 says, sketch a graph of motion, distance as a function of time, which means distance is on your y, time is on your x. That's the thing better. That would correspond to the following bicycle trip. You start your bicycle from rest, increase your speed until you reach a comfortable traveling speed. You continue with the speed for a few minutes and complete your trip by slowing down uniformly to a stop. I'll just squeeze it into a blank one here. All right, so we got a distance as a function of time. So time and distance. Displacement time graph. You start from rest, likely from the origin, and you increase your speed until you reach a comfortable traveling speed. So what does that look like? Curve. With the curve part shows increase in speed until you reach a comfortable traveling speed. What do you mean doesn't matter? No, it doesn't matter. No, they don't give you any time. So they just want to sketch. They just want the shape. So now we're going to continue at I'm going to decrease that because it felt a little bit. So now it's going to travel at a straight line. And then eventually it slows down at a uniform rate. And then becomes flat, right? Pretty simple road. What would it look like if they decided to speed up and return to where they came from? It'd be like exactly, right? Like that. Okay. So after all that, you should have your brain cells, your memory of velocity, acceleration, graphs, and all that good stuff should sort of be maybe not completely 100% back in shape, but at least energized and ready to roll. Get some new stuff. Okay. So what I did on the weekend was, because I realized after all these years that I should do this, I should probably review some problem-solving techniques.
Sure.
What I did was kind of look at the Rampton flowchart for grade 11 and sort of picked out all the formulas that I know you're going to need sort of in the future. There they are there. Your old favorites. And I realized I kind of cut and pasted and it didn't really work out so well. I was kind of in a rush, so I probably got to clean this up a bit, but it'll have to do for right now. So V bar equals D over T, that's an old one from grade 10. V av, which is really just, what? V bar. I'm not sure why Tyler put it as V av. V bar is V1 plus V2 over 2. What are the funny little things over top there? Over V1 and V2. He just put vector symbols over top, so just ignore that. It's V1 plus V2 over 2. Delta V is Vf minus Vi, change in velocity. A equals delta V over delta T. F net equals Ma, there's an old goodie. And mu equals Ff over Fn, probably your favorite formula, right? And it's smiling because it's just curve base. Okay, those are all ones from grade 10 and 11. And we're going to be moving forward, and probably tomorrow I'm going to dazzle you with my algebraic skills. Your 11 years of math are going to be put to the test, and you're going to think, wow, your brain is going to explode with fascination, I guess. So I'm going to take these formulas, and I'm going to do a few grade 11 problems with just sort of get you up to speed, little pun there. And then probably tomorrow I will do the, thanks Jessica, I'll do the formula derivations, the grade 12 formulas that you've heard so much about, I'm sure, right? You guys probably talked about it all summer. Okay, here's some reminders of how to solve problems. I will say this, there's probably more problem solving in grade 12 than there is in grade 11. Probably less theory, more problem solving. Read the question once, and read it a second time, identifying quantities and what they represent. What do they mean? Identify what the question wants you to find, because quite often I find students don't actually answer the question. And then work backwards through formulas to develop a roadmap. I started doing this with my second semester last year, right? Kind of giving me that backwards thinking kind of thing. Remember doing that? Some of you? Shall we try one? Again, these are all questions that I pulled off grade 11 sheets, so you should have seen these before. Do you want to try one on your own first?
No.
Just what I expected. A bunch of no's and a few yes. You know what? You go ahead and try. I'm going to do attendance anyways. It's not going to hurt you to try. You guys try. I won't be long. Okay, got a mass of 1,600 kilograms. Some of you might benefit from this, right? Some people just do this. That's okay too. But force is required to give it an acceleration of 1.2. Acceleration is 1.2 if there are frictional forces totaling 200 newtons. Friction force is 200. What are they asking for? What force is required? What are they asking for? Applied force. How much force has to be applied? Well, I got M and A. What can that give me? That can give me F net. Do I need to find F net? No, but if I find F net, I'm kind of sort of working forwards here, I guess, right? Because I see I got M and A. If I got F net, then I can use that to find FA, right? How do I find it? Using F net is equal to FA plus FF. You're right, you don't. But is that really a formula? I mean, you can put it on there, but really, F net is equal to FF is really just an application of the net force is force 1 plus force 2 plus force 3. Like, is not just net force means the sum of all forces? And if there's only an applied force and friction force, well, then that's the only force there are, and so that's the formula. So in that sense, it's not really a formula, it's just an application of a definition, I guess you could say. But that's okay. Okay, so let's find the net force. F net is equal to MA, and again, I'm encouraging you to write the formula. I don't think there was anyone in the room that was bad at that. And then right underneath, line up your equal signs. The mass, 1,600, 1.2. 1,800? 1920. That sounds more familiar. I had hoped my handwriting would improve over the summer, and once again, for the 25th year, it's not come true. I should practice. 1920 is the net force. Now, a lot of kids will just go 1920 minus 200, done. What's wrong with that? Maybe it's right. Is it right? Wrong. That's what happens when you don't write the formula. Because the formula really is, or the expression, I guess, F net is equal to FA plus FF. And what is the net force? 1920. Write it underneath. We are solving for the applied force. And the friction force is 200, but it's really minus 200. And when that minus 200 goes to the other side, you get an applied force of 2120 newtons. How come it's more? It takes more. You need 200 newtons of force to overcome friction, plus a net force of 1920. 1920 goes towards the acceleration. The 200 goes towards friction for a total of 2120. Will the applied force always be more than the net force? When there's friction involved. Want to try another one on your own? Come on, you guys. You want me to read it for you and get you started? How about we do that? I'll read it for you and get you started. Object of mass 50 kilograms. At rest at the origin on a horizontal frictionless surface. At time t is equal to 0, a force of 10 newtons is applied to the object in the horizontal direction for 5 seconds. So, my applied force is 10, and that time is 5 seconds. What are the position and velocity of the object at t is equal to 5 seconds? And if the same force is again applied at 15, you know what, how about we deal with part B later? What are the position and the velocity of the object at t is equal to 5 seconds? So we're asked to find the velocity and the displacement. It starts at 0, we're looking for position. So the position is equal to the displacement. Okay, well, once again, I've got M and T and A. What do I do? Is my FA equal to my F net? It is. How come? Frictionless, right, Shelby? So now I have F net and M. That will give me acceleration. And with acceleration and time, I can get change in velocity, which is equal to the final velocity because it started at rest. And then the position, how am I going to get position? Displacement. I need average velocity, don't I? So I'm going to have to find average velocity, and that's going to give me displacement. Oh, there's lots to do here. Do you want me to do it, or do you want to try it? I know I can do it. Net force is 10 because it's frictionless. F net is equal to MA. 10 is equal to 50A. 10 over 50, 0.2 meters per second squared. With me so far? Okay, so with my acceleration, now I'm going to find my change in velocity. Delta, oh no. A equals delta V over delta T. 0.2, change in velocity. Time is how much? 5 seconds. 0.2 times 5, I think, is only 1. The velocity changes by 1 meter per second, but what was it to start with? We didn't actually say that, right? The initial velocity was 0. So because the initial velocity is 0 and we change by 1, then that means that our final velocity is 1, right? Wouldn't it be nice if we had some way to sort of not always have to deal with that? That's coming up tomorrow. Brand spanking new formulas for it. So that tells me go back to the question, position and velocity. So yeah, But now I want to know the position. First I have to find average. Remember doing this last year? Initial is 0, final is 1, giving us an average of 0.5. And now I can go with V bar is d over t. Average velocity is 0.5. We're looking for d. The time was 5 seconds, 2.5 meters. I will tell you this, that with the formulas that I show you in the next day or so, all of this will be simplified. We're going to sort of be able to condense. We're going to basically be doing the algebraic manipulation. We're going to sort of be combining these steps here. It's quite nice. If the same force is again applied at 15 seconds, what are the position and velocity of the object t is equal to 20? Okay, I think we should draw a picture. 0. Run out of space. 5 seconds. And then when is the force applied again? At 15. And then at 20. I apologize. I didn't realize how much space you needed. Is the back side, have you got space on the back? Is there a question there? You might have to go to loose leaf. I apologize. Okay, so we know that it's at rest at 0. How fast is it going right here at this 5-second point? It's going 1, I think, isn't it? Right? 0.2 was the acceleration. So it's going, I'll do it in a different color here, it's going 1 meter per second here. And it's traveled how far already? 2.5. What's happening between 5 and 15 seconds? It's continuing at a constant rate. What is that constant rate, Laura? 1 meter per second. In fact, we could probably do this part in our head, I'm hoping. Like it's traveling 1 meter per second for 10 seconds, right? I mean, really, this is an application of V bar equals d over t. It's traveling at a constant 1 for 10 seconds, and so it goes 10 meters here, right? But then what happens? Why does it go 5? The average velocity, it's staying at maintaining at a constant 1, right? This is the average velocity for this bit here. That's actually a good point. I hadn't really spotted that. This 0.5 is the average for this interval, but the average here is 1 because it ends up at 1. It's not accelerating, so it remains at 1 throughout the entire distance. What happens here? Speeding up for 5 seconds. And it's the same force. So if it's the same force, would it be the same acceleration? How come? Because the mass didn't change, right? The same 10 newtons here. Are we going to just rewrite this step? You can if you want, but what are you going to get? You're going to get the same acceleration, right? So the acceleration here is 0.2. The only difference is, I was just about to say, does it travel 2.5 meters? Does it? How come? Because it has an initial velocity of 1, right? It has an initial velocity, so the average is going to change here. So let's just do this. Let's go A equals delta V over delta T, 0.2 delta V. The time, again, is 15 to 20. Oh, so that's going to be the same. The delta V is 1. But the final is not 1 because what did it start at? It started at 1. So in fact, wow, this is a longer question than I realized. You're the first class that I've tried this with. Don't you feel special? What's the initial velocity? 1. So that makes our final velocity 2, doesn't it? Take that minus 1 to the other side. It started at 1 meter per second. It changed by 1. It's now going 2. Which makes our average what? Oh, actually the question was, let's go back to the question. What's the velocity of the object and the position at 20 seconds? So that is the part B answer for the velocity. But the position, how far did it go? What's the blue value here? Well, average is equal to VI plus VF over 2. The initial was 1. The final was 2. It's going to be what? 1.5. Yeah, bigger than I realized, you guys. What's the time? What do I use for time? Was it you, Renee, that said to use 20 seconds?
Well, yeah.
How much time has elapsed? It's not the time, it's the time interval, so it's 5 seconds. So in fact, the displacement is 2.5. Hold on here. Oh, I see a mistake I made. Oh, no, hang on. No. Oh, yeah, 1.5. Thank you. I was looking at 7.5. I knew it couldn't be the same. 7.5. There we go. But that's just what? That's just the interval of that there, right? So the final question, which says, what's its position? And I'm going to wrap this up. What's the final position? 2.5 plus 10, 12.5 plus another 7.5. I think it's 20, isn't it?
Yeah.
Final position is equal to 20. Wow, that's longer than I realized. But I will say this, we can do that with grade 12 formulas a whole lot quicker. You just have to go through all the algebraic steps. I got 2 more, and I just sort of randomly picked questions. You guys want to try this one? How about I draw a picture and get you started? Come on. No? I'll get you started. Father's pulling his son on a wagon. He pulls with 200 newtons of force at an angle of 25 degrees above the horizontal. Remember those kind of things? Does it matter if it's a girl or a father pulling a wagon? Oh. 200 newtons. What's the angle? 25 degrees. There is 40 newtons of friction present. 40 newtons. The boy and the wagon have a mass of 35. What is the acceleration? What do we do when it's at an angle here? Yeah, and in fact, I'm going to do my absolute best because I've realized that by calling it FH, I've created an inadvertent error in students' minds. So I'm going to call this FA. And for those of you in second semester, you started seeing this. First semester, people didn't see it, but I'm going to call this FAX. And I think Mr. Smigowski uses that term. And when I thought about it, I thought, you know what, that's better. Because it's the X component of FA. It's the X component. Some of you might want to call it FH, and you're going to see FH still in the solutions because I'm not going through them all to change it. But FAX, right? X component. How do we find the FX or the X component? Cos. How come? And the adjacent. Right. Yep. So it's going to be FAX is going to be FA cos theta, I guess. So 200 cos 25. And calling it FAX actually leads me into another topic in about a week or so, which is vector components, which helps. So I'm going to start calling it that. Someone's got to help me here. I don't have a calculator. I can do a lot of math in my head, but I can't do trigonometry. How much? 2.6, Dan? We'll say 181.3. Remember, your calculator has to be in degrees, right? So of the 200 newtons, 181.3 goes into pulling it sideways. Is that the net force sideways? Is that the total force sideways? No, because it's in fact 4 newtons of friction, right? I guess this is going to be FAX. We're going to say plus FF, but keeping in mind the friction force is negative. 181.3, that's going to be minus 40. So I get here 141.3. Okay. Now, I didn't really come up with a plan yet, did I? I sort of just jumped right in, because I just tend to do it. What's the acceleration? I got the net force, don't I? Do I have the mass? Yeah. Imagine if I showed grade 11s of stuff right at the start. You guys know that you've been through this, and oh yeah, you may not be able to do it right now, but you know you've been through it, and it's going to take you a little bit of practice, and you're going to be good, right? I showed this to grade 11s. Have you guys improved since grade 11, the start? Yeah, think back, right? You've come a long way. Someone do this division for me here. 4.04? 4.0.
I was told in university you have to use every decimal place during your exam.
They're going to tell you in university, they're going to give you the big significant figures thing. Did I give you the significant figures rant last year?
Yeah.
Don't like them? Big waste of time.
I like
You like them?
Is that one?
It's where you have to, here's what you would do. 200, I don't know how to deal with sig figs with a trig. I don't. I would imagine, see, I guess, significant figures, there's only so much accuracy in each one of your measurements. So there's actually, technically speaking, this has one sig fig because it's 200. The zeros don't count unless it's a decimal, unless there's a decimal in it. So there's one sig fig here, there's 2 sig figs there, which means you can only have 1 sig fig in your answer, so it's 181.3, which means, guess what? The answer here is going to be 200. You round it up.
So what is that?
No, I am not doing that nonsense. But that's what they're going to get you to do in university. And what happens is, in my humble opinion, and I can certainly be wrong, I'm wrong daily, but I believe that if I teach sig figs too early, all you guys worry about is sig figs, and none of the other stuff is going to come into play. So, the few of you that are going on to university physics are going to have to deal with sig figs. The rest of you, who cares? Any kind of math, any kind of science, they're going to teach you sig figs, and you're going to be fine. Are they going to teach sig figs in university, Mr. Burnett?
Nope, but they're going to force it.
Okay, so here I got a question for you. This has never come up in all my years. I got a mass of 200 here, or sorry, an applied force of 200 newtons. I got an angle of 25. So how many sig figs in the 200?
That one?
Yeah.
One.
How many sig figs in the 25? So should this not be 1 sig fig? So my answer is 200.
Yeah, so I just rounded 2 decimals.
there's my point. Why? There might be a special rule for trigonometric sig figs.
I will say this, in chemistry at the U of M, the rule was we had to keep all of our...
Okay, so we got an acceleration of 4 here. How far has the wagon traveled after 6 seconds? Now, in grade 12, that's going to be a one-step problem. Yeah, we're going to have to do more than that. I know. Grade 12, one step. It's going to be awesome. I should, in fact, you know what? After I do those formulas, make me come back to this question. I'll show you how easy it is. For us, though, we're going to have to go, I guess, to get how far, we're going to need V bar. We got to get VF from acceleration. A equals delta V over delta T. 4 is equal to delta V over 6 seconds. The change in velocity, that's a 424 meters per second. V bar is VI plus VF over 2. Man, I hate doing this, but I know that I can just use those formulas. 0, 24, 2. The average is 12. And now V bar is D over T. 12 equals D. What's the time? 6 seconds. 72. Again, I can do that in one step.